Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi all, so welcome to the next part. Now I guess he's going to talk more about how to select these users and how to get more throughputs out of this MIMO.
So why user selection is important? Okay. It is because this capacity is really heavily depends on the MIMO channel structure. To illustrate that is by say how this zero forcing does. Okay. So basically we consider about the X point, they have 3 users, okay, A, B, C. And we need to pick up 2 users. So when we consider about zero forcing decoding, basically we can consider about assuming the channel of A is in this vector present channel. And this vector presents the channel of B. Okay. So to decode the signal of A, we need to do a projection. It's basically the zero forcing, how the zero forcing does. We project to the orthogonal direction of the channel B. And because it's a projection, actually there's a reduce of the signal stress. So this is a loss because of the zero forcing decoding. So we cancel the self-interference, actually pay a price. This price is reduce your signals strength as a power. Similarly, if you're decoding this B, actually you do the same projection and reduce the signal strength. So now we can observe that the angle of these two channels, okay, really determine how much loss you're going to have in your after you decode. Okay. So obviously this is A and B and the B and C. B and C, these 2 channels are more orthogonal to each other. That means they are more wider angles between these 2 channel vectors. Then choosing this one will get better performance because they will have less reduction in the channel. Okay. However, if we do a random selection, okay, then we do not really control pick up which one. We just random pick. Okay. Sometimes we're going to pick up the good ones. Sometimes we're going to pick the bad ones. Okay. So we get the average. And with the more antennas, actually we have more components to pick. Okay. If you random pick that, more likely we get these bad ones instead of get all these good ones. So this is the performance comparison is that. So this white block presents you random selection, just a random pick, okay. And this dark ones basically presents you strategically pick the best one, okay. Then you can see a huge difference between these 2 strategies, okay. With random selection, you basically cannot make full use of your capacity, and the capacity even drop with more antennas. Okay, with more antennas, the random pickups users simply does not work. So, ideally, we want to get this. Okay, we need to select these best users, combine them together. That means their channel are more orthogonal to each other. Then we do the decoding. We do not have this loss of signal strength. But actually compute such optimal compilation of your mobile users is very hard. Okay. It's actually need compilation complexity to pick up. Because you need to examine all these compilations of these mobile users. Okay, so there are too many compilations. And because we want to examine this channel capacity, actually we need to compute this channel inverse. Okay, and this is a nonlinear operation. So it's not easy to find any approximation algorithm to do this. Okay. Now let's consider. So you say, okay, fine. this is exponential complexity. But in practice, not all exponential complexity algorithm cannot be performed in reality, right? So first we need to consider how much time we really to compute these channels, okay? But say the result is really lacking because they're going to give you need affordable computation with only a small number of users to pick up, and with a medium-sized MIMO system. So this is number of potential users you can choose from, okay? And each line, this circle means I have 2 antennas, and this one is going to have 8 antennas. 8 antennas is not really large scale; it's a medium scale MIMO system. So you can see, let's consider about 8 antennas. When you have this 30 number of users, it's going to have like 10 seconds to compute, to select all these users to get best one. So this basically cannot do this, right? So we need to reduce this computation overhead. Okay, we cannot do this. It's too much computation. But one obvious way is that we can consider, okay, if we can, because previously this is a compilation of how much you search and how each computation you spend to compute a inverse of the channel to get the capacity estimation. So one idea is that actually we can reduce the overhead of channel inverse. So the idea is actually quite interesting, and in previous some paper also explore if we can do something like exploration, like say we only sample the channel and then pick up a few sample subcarriers and do the channel inverse, and use this channel inverse to get approximate of nearby subcarriers. Okay, so that's a basic idea. So we did a few experiments. Actually, we found that this is not really good because if we pick up 1/2, that means we just remove half of the subcarriers, and it only compute the channel inverse of half the subcarriers. We got, in a stable environment, we got 2 dB loss. Okay, because it's error in this approximation. But it's okay. 2 dB is okay. 3 dB is fine. And but now if you only pick up 1 of 5 subchannel, then we get as much as 6 dB. But you with a slight movement, okay, then it becomes very, very bad. The problem is because there's multipass feeding, okay, so make some very sharp transition between one subcarrier and another subcarrier. So although you can save some overhead, but I'm not suggesting that's the way to go because it loses a lot of SNRs because of this approximation. So the better way we think it is to reduce the search space. Okay. Instead of doing like this exponential search, we want to bound the search, the computation, the search computation. We want to bound that. So we come up with a branch and a bounding idea. Okay. So it's trying to search the tree, expanding, like searching is like expanding the tree of the searching tree. So they come from the root, then they pick up the first user in the beamforming group. Okay, so pick up user 1, each one, and they examine that, and the span in level span if how is by user 1 combined with user 2, and the user 2 with user 3, and so on and so forth. Okay, so expanding the tree to compute. So if you explore the entire tree, then again we just try every compilation of the mobile users. But we need to control this bound. We actually each time we only select the top k groups. Okay. So for example, in here we just expand. So U1 you compute to UC and find the best k. Okay. Then we search from the best k to span the next level. Okay. So each time we constrain the computation and to computation. So we bound this computation to search the tree, and some bad nodes simply we do the prune at the early stage, so we do not expand on that.
What's the criterion for the first level? You don't have any projections, right? There's only one user.
This one? Yeah, each one you can consider that means the SNR of each user is a constant. Then after we generate the trees, actually we do not discuss this result. We save that in a database. Okay. Then we do that. We can do them a progressive update. So the idea is that actually you do not need to compute the group every time you transmit a packet. We update this group result, this tree, only when some channel changes. Okay. But we know that this channel we can consider as a constant during the channel coherence time. So we need to only get the one update every channel coherence time. Then we just update these trees. So if this tree, if some certain user change, only affects this portion of the subtree that contains this user. So we just update this smaller portion of the trees. So then this also saves the whole computation. So in overall, with this K, actually provide us a tuning loop. It's a tuning knob that control the trade-off between how much computation you spend on finding the optimal, finding a better group, and how suboptimal group you can get. Right? So it's basically a trade-off between the sum rate improvement and the complexity, the computation complexity you spend on that. So actually we evaluate that. So this is a processing time, and this is this brush and bounding algorithm over the best one. This is optimal. We explainly search the whole compilation and get the best one. And we found that actually a few keys. Okay, you do not need to keep much keys. Only a small number of keys, then we can pretty much close to the optimal ones. Okay, so that means we need only to tune the key within a small range. Okay. So we implement that. So the pickup key is based on the channel coherence time. So the goal here is that we want to get the user selection before any channel, so any new update is coming from. Okay, to get a new update, we need to update the trees. Okay, so we need to finish the tree updation before a new update comes from. Okay, the new update is coming from at the coherence time, the least coherence time of the user. So actually, we use that as a computation time bound. Okay, here is that the computation time bound is 30 milliseconds. Okay, so actually we adaptive. Based on this, we adaptive how many keys we have. So actually, we can almost track to have this computation finished, the tree update before the deadline occurs. So that means every 30 milliseconds we're going to have the new update. But the fix, of course, sometimes you just do not use the time very well. You spend less time to compute that. Sometimes you just spend too much time over that, so it's not very good. So with that, actually we can. So this is the evaluation of the really sum rate we can get with this greedy algorithm. So this is random, so it's just a random pickup user. So it's really bad. And a greedy algorithm basically means each time I just pick up the best group and drop all the rest. Okay, it's equivalent to k equal to 1 case. Okay. Now its performance better than greedy, but it's still far away from the optimal. So this this line is our optimal exclusive search. Now we find that this adaptive K stage, so you give you a little bit tunable on this, how many computation you pay on that. Actually track this optimal very close. Okay. That means you give me a little bit more options. Okay. Then I can do much better than you do not give only one option. That option is greedy, is only one option. But you give a little bit more options, spend a little bit more computation on that, then I can do that close to the optimal ones. So this is another figure to show the same result, but with different clients. Okay. So the conclusion is still same, like with this adaptive choose of the computation K is pretty much close to the optimal user selection. Okay. Okay. So like yes. So I just summarize this part. So let's say there's a MIMO. We're talking about the scalable joining. Now I just give very quick discussion on the user selection. So basically, user selection actually from a talk this afternoon, from last talk here, actually we use this user selection. One is random selection. Okay. So random selection is simple. Okay. And in some sense, if you over-provision your transmitter antennas, it still can scale, but scale in a very low slope. Okay. So you cannot make full use of user or antennas, but it's simple. So if you consider about, I do not want to add more complexity on that, it's still a valid solution in practice. Just a waste of some capacity, but if I can make very cheap antennas, okay. Probably you can think of if I can make very cheap antennas, I do not care really the efficiency. I can just deploy very, very antennas. Okay, so that's one way to think about this. But another one, if the antennas are quite expensive to deploy, then we consider more to make better use of all this antennas capacity. Then we need some this searching algorithm to pick up the right user compilation, this user group to transmit. And this pretty much close to the optimal, and it's going to be a good trade-off between the complexity and the efficiency. Okay, yeah, please.
See, the other speaker, Bhaskaran Raman, particularly in the context of Wi-Fi, he said that MIMO is just an intellectual curiosity. he said that channel bonding and the frame aggregation are possibly more practical solutions than MIMO. What do you think?
I think to some extent, yes, sure. I think this from the practical point of view is that mostly we just pick up these most simple solutions that solve existing big problems. Definitely, I think that it's the right time when we deploy the aggregation, we deploy there's a simple technology like readaptation. But the problem is that actually we already almost achieved this stage, right? But the whole question of the research is how we push the state slot to the next stage. Okay. So this question is like, how can we increase the wireless capacity, Wi-Fi capacity, by another order of magnitude? I think the MIMO probably maybe the only way to go. Right? So I think it's still valuable to push in this way.
Yeah, with the single pair of antennas, you only go so far. It's a limit. The other thing that MIMO does is it gives you more. The other thing that MIMO does is it gives you more reliability if you're using one stream across many spatial paths, right? Which you cannot get with just a single pair of antennas. So MIMO does things fundamentally that single input, single outputs cannot do. Also at a very high level, right, I think
There are multiple issues here. I mean, one thing is, of course, physical layer, getting it good is good thing. But one of the things Bhaskar was also talking about was what about the higher layers? In the sense, for example, MAC is not perfectly designed, TCP does not. So all these things are there. But that also means there's a lot of research opportunity in terms of figuring out what we should do on the upper layers to make this work better. For example, I mean, user selection is still lower level, but how do we improve the MAC? How do we sort of, so there's a lot of research challenges there.
Yeah. So I think that we still not go to that far, so build a large MIMO system, but we think the research built around is at a building block. And we put more knowledge on the physical layer, more knowledge on the management, on the MAC, and how the TCP behavior is going to happen. I think when all these issues have been solved, then probably we have the practical system that really take off in the practical production network. Yeah, but this isn't our hope. Okay, at least.
But it's at a level, I think the PHY layer has seen the most sort of explosive improvements, and the rest of the layers have been lagging behind quite a lot. That is true, actually.
What is the scene when you consider multiple access points and you have some kind of a virtual MIMO kind of a scenario?
Yeah, I think that this is also a very good question, and I think there's a different line of research taking on that. I think these distributed MIMO have their different challenges. One particular challenge, actually, I can think of. I have worked on this a little bit with my students. Is that how you synchronize the clock between all these distributed? Yeah, that's a really challenge. And for the MIMO, if you do not have a closely synchronized clock, it's going to be a disaster. Yeah.
When you have large number of antennas,
Yeah.
did you consider the spatial correlation?
Spatial correlation
Yeah, among the
between
antenna elements and the channel within the
Yeah,
channel?
yeah. So I think this user selection is particularly to address this problem, because I need to pick up the users that their channel do not collect too much to each other, just pick up the best ones. So the idea is that, so why you think about why you pick up users actually make, so we know that zero forcing is not capacity achieving decoding MIMO, okay? We have some dirty paper. But if you consider of a selection combined with the zero forcing, they could got a optimal solutions. Basically consider about you have a large pool of users to select. That means you can always pick up these users. They only have these orthogonal channels, then you achieve the channel capacity. Okay, so that's why you think that with the user selection plus zero force, it can be a capacity achieving MIMO processing for the. Yeah.
But there are some MSC precoding is there something it may work better than zero forcing.
I think MSC is almost the identical. So they now change because in high, so it depends on the SNR, right? In high SNR, I think they don't have much difference. In lower SNR range, then consider noise, they can give you a slight better performance, of course. But they do not have fundamental change, fundamental difference from one to another. Yeah.
And the precoding, zero forcing precoding we have done.
Yeah.
If you use, suppose you do limited feedback precoding, when you have to take one kind of precoding matrix among the say n, how does it change?
Your question is how to compute the precoder based on the channel. So is that your question?
My question is that zero forcing precoding.
Yes.
You have used the instead of you do the limited feedback precodings.
Yeah.
So how does it change the performance?
You mean if you do not have this immediate feedback from the channel state?
Limited precoding means you choose the precoding matrix among the
Oh, okay. Okay. So you have a set of, So the question is that so instead of you compute the precoder on the fly, you can have a few preset precoders, and you just pick up one.
Yeah.
Pick one. Yeah, I think this. I don't do the detailed numeric comparison between these three. I think the scheme you mentioned is a lot of that being talking about the standard IoT standards. They think about how to design the precoder and so on. So I don't compare that, but I think that this could be. So this is my understanding. So may not be correct, but my understanding is a trade-off between the complexity and the performance. So definitely, if you have the precise channel state, you can get better performance in terms of sum rate, in terms of capacity. But definitely, you need to pay more computation to doing that, and adding the complexity there. For example, how you need to handle this reciprocity to make this CSR acquisition scale. So if you cannot do this, maybe it's too heavy to do that. Now the precoder may be a good solution. You can create the capacity a little bit with a very low overhead, complexity. So I think that's basically a trade-off. Okay. Yeah. Is that a question? Okay. Okay. Yeah, you have a question?
No, I don't know.
No. So I'm going to continue with the next. Okay. So probably I just in next half hour, just talking a little bit on the dynamic spectrum access. Okay. So the motivation is, okay. So currently, this spectrum basically has the ready allocation as standard by just governed by the government. Okay, and we know that it's efficient. So some spectrum basically fully utilized. It's very congested, and some portion of the utilization of spectrum is very low. Okay, almost empty. And also, currently the wireless standard, they usually have the fixed definition of your channel. It means by channel means central frequency and their bandwidth. Okay. So this fixed wireless signal is called inefficient if this channel is shared by heterogeneously wireless devices. What this means is it gives this figure gives the example of that. So consider about the AO2.11n channel. Okay, so this has 40 megahertz. But this channel is ACM band, so it's shared between the Wi-Fi and potential other radios like Zigbee. Okay, Zigbee is very narrow than radio. So if there's only two radio, Zigbee radio here. Okay. Now, how Wi-Fi pick up the channel? You cannot use the 40 megahertz channel because it's going to interfere with the Zigbee network. And the only way with current standard, we can only do with this no half of the 20 megahertz channel. But left this portion and this portion unused. So it's pretty not very efficient. Okay. So ideally, we need to have the Wi-Fi signal to receive their channel to follow this red mask, okay, instead of this one. So this requires quite a flexible mechanism to do this channel allocation on the flight because it's changing over the time. Okay. So one way to do this is basically this is non-contiguous OFDM approach. So idea of this ANC OFDM is I just divide the channel, the whole channel, with very, very narrow subcarriers. Okay. So now we just have a number of these subcarriers. Now, if any interference occurs, that just occurs in some subcarriers, we just turn off these subcarriers. Okay. There's more interference. I just mark these subcarriers. I do not use these subcarriers. Now, then we can just use these GRIL subcarriers for communication. This is the various solutions, and there are pretty much a few designs on this. But the issue is that it's quite complex. Right? Because we have the fixed allocation of subcarriers, but how to turn off certain subcarriers is dynamic. It's only have some interference there, then I need to mark this subcarriers. How we notify the other part that this has been changed? And when it's changed, that means the whole physical layer structure going to change. Like how you place this pilot subcarrier become problem, because some pilot may just be inferred. So if you remove this pilot subcarrier, on what subcarrier you place another pilot. Okay, so it's identically means for each interference pattern, it's kind of like a identical mode of the physical layer. So you need combinational number of physical configuration to do that. So it's basically, it's not really good to do that. How you do the preamble type, so on and so forth. So idea of the spectrum virtualization, we ask about the question. So can we really separate the baseband from the spectrum, the radio band? That means the spectrum you transmit over the air. Is there a way to decouple this? If we can do this, then we only add the interface between the baseband and the radio frequency to do this dynamic programming without changing the physical layer design. So that's the basic idea. So the architecture is going to not consist. So I have the baseband. Then we have a layer here to do this phase, this shape filtering. Based on the baseband modulation, we just reshape this, reshape the shape of this baseband waveform so that it can fit into the real radio frequency allocated bands. Okay. On the other hand, when you receive that, just collect these bands on the fly and do the inverse operation and compile with the symbols into a baseband. Now the baseband algorithm do not need to change. Okay, it just sends a signal as you on a contiguous channel and receive from a contiguous channel. The complexity of the real IF band allocation has been hid by this layer. So this layer, we call that a spectrum virtualization layer. So it's actually be located as a layer 0.5. So why? Because the physical layer is layer 1. Okay, it's the first layer. But it's below the physical layer. But of course, it is above the really analog hardware. So this is layer 0. So there's 0.5. So this is the whole architecture here, is that we have some spectrum manager that just coordinates the channel allocation. We assume that there's a manager there. And it just give a, say, your radio is just allocate certain portion of the band that it can use to transmit. Okay. Then this information is going to propagate to these receiver filters. Then you're doing this remapping. You get the signals from the physical layer, the baseband physical layer, and it ships that to the real allocation of the radio. It could have multiple radios, okay, or you can have only one radio that is shared by different physical layer. Okay, so the key here is how we can design a signal receiver function. The goal is to have this flexibility to transform arbitrary baseband signals to any allocation of the IF bands. So the IF band can be contiguous or can be in non-contiguous bands. Okay. So the principle is basically physical layer agnostic, we said transparent. By transparent means that the physical layer do not, with this layer, although we just translated the signals, from the physical layer point of view, it cannot tell if it has been transferred or not. Okay. Only you can see is a different channel. It could be a different channel, but so that means all the signal processing algorithm, like equalization, I think, do not need to change. Okay, that's the physical layer. And it's simple and the best alpha. So this must be stateless, very simple. So actually, the operation is basically very simple. It's only three. The first operation we call that signal decomposition. Okay, that means this decomposition basically decomposes the signal from the baseband to a couple of signal components. And these signal components just group together and change their bandwidth by adjusting their sampling rate. Okay, you can say that about how you can stretch the signal and compress the signal. And after doing that, each component may shift to a different band. Okay, doing the shifting. So then this output is going to fit on the real IF allocation. On the reverse part, it's just going to just doing the reverse. So first you shift that from the IF frequency to the certain baseband band, and adjust that according to the physical layer specification, and finally they compose all these components together and regenerate these physical layer signals as if they're going to come through a channel. Okay. So the decomposition basically involves FFT-based signal decomposition. So basically, I take the time domain sample of the baseband signal and do a large point FFT. That's basically decouple that into a set of these frequency components. Okay. And the composition is just the reverse operation. You just put these time domain samples from substreams and map that into a So we do the decomposition, then I do the mapping. Okay, the mapping to different, because we want to have non-contiguous. We just do mapping to different portion of the allocation band. Then I do a IF inverse FFT to generate the real time the time domain signals. Then these signals can be used to transmit. Okay. On the reverse part is basically the reversing is that you do the NFFT composition and pick up the signals component you want to collect for the baseband and put that into RFFT points. Then you're going to generate the domain, time domain spectrum symbols for the baseband.
So LTE does a bit of this, right? So in
Right?
the sense that LTE also does a bit of this, right? So basically it moves the...
Yeah. LTE have this single carrier FDMA. Yeah. So this pretty much similar mechanism. So it's basically idea is, yeah, I think the design is similar, under the similar inside, yeah. To decouple that into multiple components and regroup that under with certain conditions. But of course the condition is different. Then the bandwidth adjustment, this is really simple. So if you're familiar with this signal processing, is really the basic operations that adjust the rate. Okay. So basically, I want to use the mode rate and just increase my sampling to reduce the bandwidth, or reduce the sampling rate to increase the bandwidth. The shifting. Okay, shifting is also simple. Because in virtual spectrum, it always starts from 0, right? The baseband. But in physical spectrum, it can be centralized at any IF band. So I need to just remove that, shift that to a different portion of the central frequency. Yeah. So with these three operations, actually, we can do what is we can decouple a signal and map that into different bands. Okay. Then adjust each band's bandwidth to match the physical layer allocation. Okay. Then we shift to a radio front and central frequency. Then you can really transmit to the air. Okay. So But now we need to understand what is the recipient. Okay. So fundamentally, we need to consider about this is FFT decomposition, what it really does. Okay. Let's consider about this. Okay. So actually, what it does is that we do is to let's say consider what this happens. The idea is here. So let's consider this X is what we're going to transmit. Okay, and it can be coupled by its frequency. Okay, so let's doing this is FFT of this signal. Okay, let's consider the first the up portion is X1, the lower portion is X2. Okay, then we do a reshape is that we map this X1 to a higher frequency band and the X2 to a lower frequency band. Then we map this signal to two non-contiguous RF band. Okay. Then this is going to transmit over there. And then the receiver will pick up this portion, and put that into the FFT compiler and get Y. The Y is the reconstructed signal. Okay. So the idea is that we need Y equal to X. Okay. So if this to Y equivalent to X, then that means the order reshape doesn't change too much. Okay. That's it. So actually we can derive that is that actually we found the Y is something like this. It's not exactly X, but a combination of X1 and X2 with these two components. Okay. And yeah, so this one basically, it's not exactly X, but it's X plus a control channel. This edge you must have because this edge represents the processing, the channel, the propagation channel. Okay. But this part is not exactly. It have this X prime. X prime is a linear combination of this X1, X2. Okay. When it's get, if this is equal, that means this T0, okay. Yeah, this depends on the T0 is the, how to say, is the time you receive that one. So that means if you have, have a propagation delay, some kind of propagation delay to get the signals. So it's a T0. And also the FH, this is the central frequency of the first half part and the lower part. So that really means is that what you receive is not exactly the X, but a multipass version of X. Okay, it's a multipass version of X. So if it requires, if you have a very accurate time synchronization, means T0 is zero, close to zero, means it's very closely synchronized on this portion, this part, this very closely synchronized. This just equal to each other because this term becomes zero, become one. Okay, this is one, so they just X. Okay, so if there's an error, then it's called something error. It's called like a multi-pass error. Okay, but consider it's nature, right? Because this part identically goes through the different paths. Because if different frequency consider different path, so it's a reflex. So it's nature to consider. It doesn't so surprise. Okay, but this if this is not it's not. I mean, this error can be minimized if you can do the very precise, accurate time synchronization. Okay. So that's the implementation. Is actually we implement that on Sora. Okay, so it's pretty fancy system. So I like to spend a little time on that. So what we did is actually we can share, okay, as I said, we can share the radio frontend resource to multiple physical layers. Okay, so have the multiple physical layers share the same radio frontend. Okay. The idea is that actually we can directly map this DMA buffer to different physical layer buffer. So actually the physical layer have this physical app. Okay, now this physical layer we consider the app. This app basically have the virtual IX buffer. This is directly mapped to the real I buffer. Okay, but the standard buffer is different. Okay, because you cannot have the multiple file transmit at the same time, but it can receive at the same time. Okay, then the transfer buffer going to pass to a daemon here, which do the mixing. Okay, so your transmission and our transmission, if they are on a different frequency, I can just do the mix. Then we schedule the receive and transmit event and send out this mixed data out. Okay. So in this way, we enable multiple physical layers to share the same IF hardware. So there's quite a few applications. One application is that we can easily support a white space networking based on any existing file, like AO2.11g. Okay. We just reshape their width or the channel width to accommodate different bandwidth specification of TV channel. So in US, it's 6 megahertz. In China, it was 8 megahertz. Okay, in Singapore, it's 7. And it can support contiguous or non-contiguous spectrum bonding. And there's another thing we actually can enable this radio virtualization that I said in another slide is that the same radio front end can be shared by multiple baseband. So here we implement several Zigbee applications, each working on different spectrum and can receive Zigbee signals from different channels simultaneously. Okay, so now I go over a few evaluation. What we're thinking about, say, how this single link, how the performance of the reshaping, how it's working on the DSA environment, what is computation requirement to get the this reshape operations. So single link. So actually, in this experiments. Basically, we change the bandwidth. We instruct the sender change the bandwidth. So start from 20 megahertz, then go to 10, and go to, I don't know, what's this? Forget. So go to 10, we go 7, something 8, or I forget. So go to something lower and go to 5. Okay. So maybe 20, 10, and 8, and 5, something like this. Now, like I say that actually you can adapt quite well with different modulation rate, AWG or AO2.11b. You can just adapt to the bandwidth. You do not change the physical layer, you just change the operations as a spectrum virtualization layer. And this is an experiment on what we do is that actually we have this transmission, okay, there. But then we decouple that into 2 parts, okay, and leaving a hole in between. Okay, so that means this is a non-contiguous band, 2 non-contiguous bands. Okay. Then we enlarge at this clip point. We just 20 and 40 seconds. We just increase the band, this hole, by 5 megahertz. Then we see that so the throughput almost keep consistent. Okay, they have a slight difference after the shape that, but overall, it's just keep on this. So it's expected, right? Because we do not lose any bandwidth, just allocate a different band. Okay. So this is just a simple setup of a DSA network. So the idea is like we have a AO2.11g here to transmit. Now during the transmission, we have a Zigbee kicking. It's 20 seconds. Then at 40 seconds, 11B kicking. Then at some point in time, the 11B just so at this point, the Zigbee just going to end the transmission, and we allocate more bandwidth to 11B. Okay. So consider this is all designed by, instructed by a controller. So it doesn't have particular meaning here, but say controller just want to do this. Okay. Then the point is how where we can execute this bandwidth allocation. Okay, so this is the result. We just plot the throughput we can get from event G, 11B, and ZigBee. Okay, and we found that actually ZigBee just get their band and continue have a constant throughput and end. And 11G is kind of like funny. Is that going to, because it holds the 20 megahertz there, then ZigBee kick in, it just avoid that, but it still use enough 20 megahertz. So the throughput doesn't change. Until this point, the 11B kicks in, so it's occupy half of the bandwidth. Then it's drop to a half of the rate. Okay, and now it's continually drop at this point because the controller decide to allocate the mode band to the 11B. And 11B just keep on this. They do not have any transmission. And start there, they get half, and they can increase that according to this bandwidth allocation. So it's basically it's just capture on what the instruction does, the controller allocations. So one particular thing we want to examine is that because we do a lot of DSP at the lower layer, so we want to consider how much precision we need to handle. Okay, it's because it's basically digital samples we need to process. So we try to say, and for example, one particular thing we do is SAT. This is FFT. How many points we need to support? Okay, and with a different integer bandwidth, because we want to do the integer processing, integer FFT instead of a floppy FFT to increase the processing speed. This is the error, okay, in terms of dB. And I found that in general, actually, the error is pretty low, but definitely with more bits and the precision is very can be improved a lot. So we conclude that all this FFT and the shifting, all this signal processing, probably we just need 32-bit processing, internal processing, to do all these translations. So it's not really a big deal if you consider implement that in hardware. So it's integer, it's only 32-bit. So pretty much we can implement SVL as a small layer in hardware. Okay, so I just conclude that. So we propose that this spectrum virtualized layer as a general way to support spectrum programming for dynamic spectrum network. Okay. So it provides a very simple abstract to the physical layer. So now physically do not need to consider about the real allocation, the complex allocation of the radio front end, radio band, but it's only consider about it's working on the virtual spectrum that is continuously with a certain bandwidth. Okay. And this shaping is happening dynamically, so it can react very fast to the new allocation that controlled by the controller. And this also provides another way in direction that enable radio virtualization. This is previously not possible. Now with this layer, actually we can do the radio virtualization that enable multiple physical layers to share the same radio front end. Okay, so that is promising because in later we can design a wideband radio on a device, and now it can support multiple physical layers simultaneously, especially when we have this two-way radio capability on this wideband radio. That means you virtually have different, you can almost have all these physical layer radio happens on a single radio front end. Okay, so I think I just stop here. So I just summary my lecture. Talking about a lot of MIMO. I think that's a very promising area to work on, and also the spectrum virtualization area.
We have time for questions.
Please.
Many a time we have
have the band for each of them, we have the band fixed, or we have an identification number. Like even like in cellular, we really have band identification, and even in .11 we have 2.4 band or 5 band.
Right.
Now, if you choose and use a different frequency, how does a new user, like now I'm starting an wireless client, how will it know that the AP is going to send into this, or
right.
when will that trigger happen? How do we intimate I'm going to use a different frequency band?
Yeah. So I think the question is how we can pick up. We have a different, very diverse band allocation. How one can pick up. I think that's a good question, and I didn't touch that in the talk. I think in general, I think it's kind of like how we allocate this resource, right? So I mean, we can have different criteria and algorithm on that. I think there's a lot of research ongoing on this. But the point here is that probably we need some controller in the network that make the decision for you. Okay, I mean, particularly in white space, we have the concept of the database that's a market usage. So you can use this database as a container, so you can register your usage and ask for you just I want to do some networking stuff. You just give me the correct exposure. I think that's the part. And the second part is that you have the band, but the band is shared by a different radio, right? Then this pretty much handled by MAC protocol. Okay, you have a good MAC protocol and allocate the band on time. So I think that's a different could be a different solutions, a different situation. Okay. Yeah, please.
On Monday, we had one keynote lecture by Professor Sachin Katti. It was about self-interference cancellation, where the receiver, like transmission and reception, can be done simultaneously. What is that impact on the DSA? Like DSA has always been designed by planning that it will be off duplex.
I just mentioned that if you have this two full duplex radio capability, we can really enable this radio virtualization. So that can enable multiple physical layers, go through this virtualization layer, then you share the same wideband radio. Then this is one thing. I think you have this way to transmit and receive simultaneously definitely benefit the protocol design. Okay, so make you have a better protocol design, because a lot of things in dynamic spectrum access network is how we make agreement on which portion of the spectrum we use, right, from sender and receiver. If we have a lot of complexity is coming from. So if we have the full duplex radio ready there, I think that makes this kind of protocol design much easier. I think that's one possible impact on this.
I think there are lots of different. It's an open research area. I think at this point, there are lots of ways you can do. For example, when he was mentioning ZigBee and 11G and 11A all work together, you could imagine that you're transmitting and receiving at the same time. So on 11G you're receiving, on 11B you're that's not possible if you don't have full duplex, for example. So. Any more questions? I had a question actually. So let's say you are operating on 11G and you have a 20 megahertz band that you think you're using.
Yeah.
And physically you're sending on 5.
Yes.
Right? Now there are only two ways of doing this. Either you skip a bunch of subcarriers, or you make the subcarriers really narrow by dilating time.
Yeah.
So I'm guessing you're dilating time.
Yeah.
Now when you dilate time, everything increases. For example, the preamble length becomes 4 times.
Yeah.
Now all these slots, Wi-Fi slots, are designed such that, for example, then the 9 microsecond slot is designed such that.
Yeah, right.
So you see the problem, right?
Yeah.
So how do you deal with that?
I think this. So here just talking about how you virtualize the physical layer, but you consider about the MAC layer actually also lead kind of virtualized. I think particular parameters to virtualize is actually the time. So how you treat the sampling time. So currently depends on the implementation. That if you MAC layer just got the time from the physical layer, then it's not a problem, because because when you do the reshaping, it actually reclock your physical layer, and the MAC layer may synchronize. So I need to time out in like 1,000 samples. Okay, now you reclock the sample time, so it still holds the same criteria. The same criteria like 100 samples is still keep, right? But in reality, I mean, in fact, they may this time may stretch or compressed, but it doesn't matter for the.
Yeah. So where I was going to was you also need to send out the clock signal all the way to the upper layers. So you can create you can create different versions of the clock for every single.
I think it's only propagated to the MAC layer enough, right?
Yeah, I guess. Yeah. But I'm not sure what will happen in the.
Maybe for the TCP, maybe sure. Yeah. They need to tune their clock, so they do not want to time out the TCP packet prematurely. Yes, sure.
Any more questions? Yeah.
One of the issue will be from the RF front-end section, because suppose I am receiving 802.11g and there is a ZigBee is also going on, but my bands are non-contiguous. I want to receive the whole band, but then the RF front-end design will become really tough. How are you going to handle that?
You mean RF front-end what?
Because you have a wide dynamic range to capture.
Oh yeah, sure.
How do you going to handle it?
Yeah. That's also a very good question. Yeah. I think this basically requires high dynamic. So the question is like, so because you have a wideband radio, okay, then you need to capture the different wireless signals. These signals may have very large difference in their transmission signals. Then the radio definitely need a dynamic range to capture that. So I need to have sufficient bits in the ADC, so do not miss the other part. The low energy signals, which I did. Right? I think there's So the radio design, one way is basically we just build a good high sensitivity radios. Another possibility is that we can apply some filter back. So if I know some band, I don't care. I just can filter that, like a programming filter back. But I know it's still very difficult, but that's research going on there. Yeah, in general, wideband dynamic spectrum have these challenges on the radio design. Yeah, but these are hard. From my point of view, I rely on the hardcore double E guys that can fix the video design guys to fix that. Yeah.
I think in your implementation, you had 20 megahertz.
We have 40 megahertz.
40 megahertz. Yeah, it's a good question because there's LNA adjustment, all those kinds of things, limited bits in the ADC. Yeah, it's a good question.
Is any group working on that? You know?
What that?
Is any group that you are aware that?
Not. There are quite a few, and I cannot give the name long, but do a little bit of research. You can get a few people working on that. Yeah, I know a few. Actually, I collaborated with a few local university in China. They do it on the radio stuff. Yes.
Any more questions?
Okay, so then that's the picture. So actually, what I did is this is my kind of my style is that every talk is a place. I just go to the bin, image search, and search the place, and I found the first picture that I think is related to this place. So I put it here. I don't know where it is.
Yeah, this is the ISKCON temple. You can go on Friday.
Yeah. So I plan to ask you about this picture. Yeah.